Good day, everybody. Today, we'll be talking about solutions. So what is a solution? A solution is the same as the homogeneous mixture. Some students believe solutions must be in liquid phase. This is a misconception. Actually, solutions could be in any phase. It could be in solid, gas, or liquid phase. For example, an alloy is in solid phase. It's the solid phase solution. And for gas phase solution, for example, the air. In the liquid phase solution, for example, you can dissolve sugar into water. We have another special type of solution, which is gas being dissolved in the liquid. For example, in the pop soda, carbon dioxide is pressurized and dissolved in the solution of water. Late in the summer of 1986, carbon dioxide bubbled out of Lake NYOS and flowed into the adjacent valley. The carbon dioxide came from the bottom of the lake, where it was held in solution by the pressure of water above it. When the layers of the lake were disturbed, the carbon dioxide came out of the solution due to the decrease in pressure, with lethal consequences. Since carbon dioxide is heavier than air, once freed from the lake, it traveled down the side of the volcano and into the nearby valley, displacing air and killing more than 1,700 people and 3,000 head of cattle. In an effort to prevent these events from occurring again, scientists built a piping system to slowly vent the carbon dioxide from the lake bottom. Since 2001, this system has gradually been releasing the carbon dioxide into the atmosphere, preventing a repeat of the tragedy. Again, a solution is simply a homogeneous mixture of two or more substances. And we talked about the gaseous solutions, for example, air. We also mentioned for the liquid solutions, we can have a gas such as carbon dioxide being dissolved in a water solution. We can also have ethanol and water mixed up. That's a liquid-liquid mixture, like a vodka. We also have a solid being dissolved in the liquid. For example, you might have sugar dissolved in water, or salt dissolved in water to make seawater. For the solid solution, you could have a solid being dissolved in another solid, like an alloy such as brass, which is the mixture between copper and zinc. A solution has at least two components. The majority component is usually called the solvent, and the minority component is called the solute. Because water is so abundant on Earth, it's a common solvent that forms aqueous solutions. Other solvents are used in the laboratory, industry, and in the home, especially to form solutions with nonpolar solutes. When water is used, even if water is the minor component, we still usually call water the solvent rather than solute. Practice questions. What is the solute when 10 grams of table salt NaCl is dissolved in 100 milliliter of water? So in this mixture, water is used. So water usually is considered as the solvent, no matter if it's the major or minor component. For the other types of mixtures, usually the major component would be considered as the solvent. So in this case, NaCl will be the solute, while water is the solvent. Next question. Which of the following substances is an example of a solution? Remember, a solution is a homogeneous mixture. It could be in solid phase, could be in liquid phase, could be in gas phase. And the key feature is that the composition is uniform throughout the phase. So for this reason, wine is a solution, and sugar is actually a compound. Lead is an element, that's not a mixture. Both a compound and an element, they are a pure substance. Blueberry muffin, it's heterogeneous mixture, the same for salad dressing. So how to form solutions when they are dissolved in water? So basically it's a polarity match. There is a rule that's called like dissolves like. This tells you polar solvents will dissolve polar solutes, and non-polar solutes will dissolve non-polar solutes. The plus ends of the water dipoles are attracted to the negative end of the dipoles, and the plus ends to the negative charged ions. As you can see in the table salt being dissolved in water, the chloride is negative charged. It attracts the positive end of the H2O molecule, and the Na+ sodium ion is positive charged, so this will attract the negative end of the water molecules. That's how the solution is being formed. Let's expound a little bit about the solubility rules. Simply put, like dissolves like. Polar molecules will be able to dissolve in polar molecules, and the nonpolar molecules will dissolve in nonpolar solvents. For example, table sugar is a polar molecule, so this is very soluble in water. NaCl is an ionic compound, which is the extreme case of polar compound. Nonpolar solids, such as lard and the vegetable shortening, are usually insoluble in water. And the calcium carbonate, an insoluble compound, the attraction between the calcium ions and the carbonate ions is greater than that of solvent-solute attraction or the attraction between the ions with water. For this reason, calcium carbonate does not dissolve in water, and the solubility of calcium carbonate is close to 0 grams per 100 grams of water. We have previously learned the solubility rules about ionic compound in water. Let's talk about a few examples. Which solvent would be most suitable to remove grease from an object? Remember, grease is nonpolar, so you would expect to use a nonpolar solvent to remove it. All hydrocarbons are nonpolar, so E is the correct answer. In theory, which of the following would have the greatest solubility in gasoline? Gasoline hydrocarbons, which means gasoline is nonpolar. So which of the compound would have the greatest solubility in the nonpolar gasoline? That means the nonpolar molecule. For example, A, which is hydrocarbon. B, C, D, E, they are all polar molecules, so they are less likely to dissolve in gasoline. When the solution is formed, it could be saturated or unsaturated. This depends on the solubility of the compound. The solubility of a compound is defined as the amount of compound, usually in grams, that dissolves in a certain amount of liquid. A solution that contains 36 grams of table salt per 100 grams of water is saturated sodium chloride solution. So what do you mean saturated? A saturated solution actually holds the maximum amount of solute under solution condition, for example, at 25 degrees C. Solubility does change with temperature. If additional solute is added to a saturated solution, it will not dissolve. An unsaturated solution is holding less than the maximum amount of solute at that particular temperature. If additional solute is added to an unsaturated solution, it will dissolve. A supersaturated solution is the one holding more than normal maximum amount of solute, and the solute will normally precipitate from or simply come out of the supersaturated solution. So how do you form a supersaturated solution? Supersaturated solutions can be formed under special conditions. For example, you can suddenly release the pressure that occurs in the soda when it's opened. You can also change the temperature. You can dissolve a compound under elevated temperature, then suddenly cool it down. And for some compounds, it will not crash out of the solution. The solid will not be formed. Rather, a supersaturated solution will be formed in this way. What is an electrolyte? What is a non-electrolyte? Electrolyte solutions contain dissolved ions and therefore can conduct electricity. Non-electrolyte solutions contain dissolved molecules, and these molecules are neutral. Therefore, they do not conduct electricity. So electrolytes can be strong or weak. Okay. Do remember, a weak electrolyte is not the same as a non-electrolyte. A weak electrolyte will partially ionize. A strong electrolyte will 100% ionize when dissolved in water. Let's work on a few problems. Which of the following would be poorest conductor of electricity? So let's go over this in much detail. Electrolytes can be strong or weak. Strong electrolytes will dissolve in water and ionize 100%. Here's some examples of a strong electrolyte. We have strong acid. So strong acids, they're all strong electrolytes. We can have strong bases. We can also have soluble salts. For example, strong acid HCl, HBr, HI, HNO3 nitric acid, H2SO4 sulfuric acid, HClO4 perchloric acid. Strong bases, for example, lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, barium hydroxide, strontium hydroxide, etc. Soluble salts, for example, table salt, potassium bromide, etc. We can use the solubility rules to determine whether a salt is soluble in water. For weak electrolytes, weak acids, for example, hydrofluoric acid HF, acetic acid, you might have weak bases, for example, ammonia NH3. Okay. So both strong electrolytes and weak electrolytes, they are electrolytes. When they dissolve in water, they will conduct electricity. Non-electrolytes will not conduct electricity when dissolved in water. Non-electrolytes, water, sugar, ethanol, etc. So the correct answer will be C. Water is a non-electrolyte. It will not conduct electricity. HF is a weak electrolyte. NaCl, ammonium nitrate, and magnesium chloride, they all form aqueous solutions. They dissolve in water. They are strong electrolytes. The solubility of a solid solute is dependent on temperature. In general, the solubility of solids in water increases with increasing temperature, as you can see in this diagram. A common way to purify a solid is a technique that is called recrystallization. Recrystallization involves putting the solid into water at an elevated temperature. Enough solid is added to the solvent to create a saturated solution at elevated temperature. As the solution cools, the solubility decreases, causing some of the solid to precipitate from solution. If the solution cools slowly, the solid will form crystals as it comes out. The crystalline structure tends to reject impurities, resulting in a purer solid. We can use recrystallization to make rock candy. The first step, you prepare a saturated sucrose or table sugar solution at an elevated temperature, then dangle a string in the solution and leaves it to cool and stand for several days. As the solution cools, it becomes supersaturated and sugar crystals grow on the string. After several days, beautiful and sweet crystals or rocks of sugar cover the string, ready to be admired and eaten. The solubility of the gases in water will depend on both temperature and the partial pressure of that gas. When temperature increases, the solubility of the gases in water will actually decrease. We might have observed this before. Before water reaches its boiling point, you will see small bubbles develop in the water. These small bubbles are dissolved air, mostly nitrogen and oxygen, coming out of solution. As the temperature of the water rises, the solubility of the dissolved nitrogen and oxygen decreases, and these gases come out of the solution, forming small bubbles around the bottom of the pot. Once the water boils, the bubbling becomes more vigorous. These larger bubbles are composed of water vapor, not dissolved air. Henry's law tells us the relationship between the solubility and the partial pressure of the gas. The solubility of the gas is directly proportional to the partial pressure of the gas, and KH is so-called Henry's law constant, and the P gas is the partial pressure. As you can see in this picture, the gas at low pressure over a liquid, you have less gas molecules being dissolved in the liquid. When gas is having higher pressure over the liquid, then you have more gas molecules being dissolved. How is the solubility of a gas affected by the temperature of the solution? Remember, for a gas solute, when the temperature is increasing, the solubility will decrease. When temperature decreases, the solubility increases. So B is the correct answer. What happens to the solubility of a gas when the pressure above the liquid increases? When the partial pressure above the liquid increases, the solubility will increase as well. This is summarized in Henry's law. Mass percent is used to indicate the concentration of the resulting solution when you mix a solvent and a solute, and it's defined as the mass for the solute divided by the mass of the solution, which is the total for the mass of the solute plus the mass of the solvent times 100%. In addition to the parts per hundred, which is mass percent, also in common use are parts per million or ppm, the number of grams of solute per 1 million grams of solution, parts per billion ppb, the number of grams of solute per 1 billion grams of solution. So let's calculate the mass percent of 2.50 moles of NaOH in 0.900 liter of water at 25 degrees C. The density of water is 1.00 grams per milliliter at 25 degrees C. So to get the mass percent of NaOH, you would need to know the mass of solute. You would also need to know the mass of the solvent, because mass percent is defined as the mass of solute divided by the mass of the solution, which is mass of solute plus the mass of solvent, times 100%. So we already know the moles of NaOH. Moles times molar mass will give us the mass in grams. Molar mass for NaOH, so it's 1 sodium, 1 oxygen, and 1 hydrogen. You put it together, the molar mass of NaOH will be 39.997 grams per mole. You simply add the atomic mass of sodium, hydrogen, and oxygen together. So the mass of solute is the number of moles times the molar mass. This gives us the number of grams, 100 grams. Mass of solvent, water, can be calculated by density times volume. The density is 1.00 grams per milliliter. And if we have 0.900 liter, we need to convert it to milliliter by multiplying 1,000. This gives us 900 grams. The mass percent can be calculated as 100 grams of solute divided by 100 grams of solute plus 900 grams of solvent. So this is 10.0%. A is the correct answer. Another unit is commonly used in chemistry to indicate the concentration of a solution. That's molarity. Molarity. Molarity is defined as the number of moles of solute per liter of solution. Note that molarity is moles of solute per liter of solution, not per liter of solvent, not solvent, but solution. To make a solution of a specified molarity, you usually put the solute into a flask, then add water to the desired volume of solution. In the chemical lab, we measure out a certain number of grams of the solute, then dissolve it using a small amount of water. Once everything is dissolved, you can add more solvent to the line, as you see over here. Then you can cap it and mix it. Let's see one example. Calculate the molarity of a solution made by putting 15.5 grams of NaCl into the beaker and adding water to make 1.50 liter of NaCl. We need to calculate molarity. Remember, molarity is the moles of solute divided by the liter of solution. So we have grams of solute. Grams of solute divided by molar mass, this gives us the moles, as you can see over here. The molar mass of NaCl, 58.44, comes from adding 1 sodium and 1 chlorine atomic masses together. The molarity of the solution is the moles of solute, which is calculated over here, divided by the liters of solution. So this gives us 0.177 mole. Remember, M is the same as mole per liter. Let's look at another example. Determine how many grams of sucrose are contained in 1.72 liter of 0.758 molar of sucrose solution. We can treat the molarity as the conversion factor, because when you look at 0.785 molar, it can be treated as 0.758 mole per liter. Liter is related to mole of solute by molarity. Through the first step, we will be able to convert liter of solution to mole of solute. The mole of solute can be further converted to grams of solute by using molar mass. So let's put this together. We have 1.72 liter of solution. To cancel out a liter of solution, we will have to write the 0.75 mole at the top and the liter of the solution at the bottom. Then, to cancel out the second unit, which is the mole of the solute, then we will need to put the mole at the bottom for the molar mass. So eventually we get 446 grams of solute. The 342.34 grams per mole is calculated through the formula C12H12O11. You put together all the atomic masses for each element. You can arrive at 342.34 grams per mole. Practice questions. What is the molarity of NaOH in a solution containing 40.0 grams of NaOH in 750 milliliter of solution? To calculate the molarity, we need to know the moles of the solute. We also need to know liter of the solution. So the moles of solute can be calculated by the mass divided by molar mass. The mass is 40.0 grams. The molar mass for NaOH is close to 40. It's 39.997. This molar mass can be calculated by adding sodium atomic mass, one oxygen atomic mass, and one hydrogen together. You will have 39.997, which is close to 40. Okay. This is divided by the volume in liter. 750 milliliter is converted to liter by dividing by 1000. So this will give us the molarity. The calculated result is B, 1.33 mole. Previously, we have learned when an electrolyte dissolves in water, it will ionize to make ions, and this is the very reason why electrolytes conduct electricity. The ion concentrations for a strong electrolyte can be easily calculated because strong electrolytes always ionize 100%. For example, for calcium chloride, which is a strong electrolyte, this will ionize 100%. So for 1 molar of calcium chloride, it does dissolve in water to form aqueous solution. It will ionize to calcium ion and twice as much chloride ion. If you have 1.0 molar of calcium chloride to begin with, then afterwards everything will be converted to the corresponding ions. Since we have a 1-to-1 ratio between calcium chloride and calcium ion, so eventually you will have 1.0 molar of calcium ion, but since it's a 1-to-2 ratio between calcium chloride and chloride, so you will have 2.0 molar of chloride concentration. This calculation is based on the ideal situation, so they are just the approximations, because when ionic compound dissolves in the solution, some of the cations and anions may pair up, so the actual concentrations of the ions are lower than what you would expect if you assume the complete dissociation occurred. Let's work on a couple of examples. Determine the molar concentrations of sodium ion Na plus and phosphate PO4 3- in 1.50 molar sodium phosphate solution. For sodium phosphate solution, once sodium phosphate dissolves in water to form an aqueous solution, it ionizes 100% in the ideal situation. For every mole of sodium phosphate, 3 moles of sodium ion will be generated, and the 1 mole of polyatomic phosphate PO4 3- will be generated. For this reason, because it's a 1-to-3 ratio, you have the molarity of sodium 3 times as much as original. So you have 4.50, and the molarity of a phosphate is 1-to-1 ratio. That's why it's the same as the original. A solution can be made from scratch by measuring out a certain number of grams of solute, then dissolve it in a volumetric flask, as we showed you before. It can also be made by diluting a concentrated stock solution. To determine how much of a stock solution to use, you can use the dilution equation. M1V1 equals M2V2. Because M1 times V1 tells you the number of moles. M times V gives you the moles of the solute. Since before and after the dilution, the moles under these two conditions, the concentrated and diluted conditions, they have exactly the same number of moles, which is given by M times V. So that's why M1 times V1 is the same as M2 times V2. As we just emphasized, this equation works because the molarity multiplied by volume gives the number of moles of the solute, which is the same in both the solutions. When diluting the acid, always add the concentrated acid to water. Never add water to the concentrated acid solutions. It could be dangerous. Let's look at one dilution problem. Prepare 5.00 liter of 1.50 molar KCl solution from a 12.0 molar stock solution. So we use the dilution equation for two different conditions, the concentrated stock solution and the diluted solution. We need to find out the volume V1. So V1 is M times M2 times V2 divided by M1. Substitute the numbers in, then we figure out we need 0.625 liter of stock solution for this purpose. So in practice, you first add 0.625 liter of 12.0 molar stock solution into a volumetric flask. Then you rinse off the residual amount of stock solution from the graduated cylinder, then add it to the line. Next, we are going to talk about the solution stoichiometry. Previously, we have learned something that is similar. For example, for a chemical reaction, we have learned you can derive the molar relationship between a substance A and substance B. That's the core relationship you can always derive from a chemical equation. If the grams of A is provided and you want to figure out the grams of B that can be generated or needed for the reaction to go to completion. Let's look at one practice question. How much of 0.125 molar NaOH solution do we need to completely neutralize 0.225 liter of 0.175 molar of H2SO4 solution? In this particular question, we have a balanced equation over here. The most important thing you should first start with is the molar relationship for any chemical reaction related calculation. Here, the mole of H2SO4 is given, and we ask some information about NaOH. For this reason, in the solution map, the core relationship is going to be the mole of sulfuric acid being converted to mole of NaOH. That's the core relationship. Do remember, moles can be converted to liter using molarity. So a liter of sulfuric acid can be converted to moles of sulfuric acid. And since we need to find out how much in terms of volume of NaOH we need, so we need to further convert moles of NaOH to liter of NaOH. Step 1, we convert the liter of a sulfuric acid to mole of sulfuric acid. Step 2, we convert moles of H2SO4 sulfuric acid to mole of NaOH. Step 3, we convert moles of NaOH to liter of NaOH. Let's do this stepwise. We are given 0.225 225 liter of sulfuric acid. So the first step, we want to convert this to mole of sulfuric acid. So for this reason, mole of sulfuric acid is going to be over the top, and the liter of sulfuric acid should be cancelled out. But what number should we put over here? Do remember 0.175 molar is the same as 0.175 mole per liter, or you can write the liter over the top, liter 0.175 per mole. But we need to cancel out the liter, so for this reason 0.175 should be over the top. This is step 1. For step 2 here, we need to convert this mole into a different mole. So to cancel out this mole of sulfuric acid, we need to put the mole of sulfuric acid at the bottom, so these two units can cancel out, and we can retain the mole of NaOH. Now the question is, what number should we put before these two moles? Remember, these two moles come from the mole relationship, which is directly derived from the balanced chemical equation. So when you look at number of moles of sulfuric acid, in the chemical equation we have 1 mole. So that's where you get that number. It's 1 mole. So it's 1 mole and over the top we have 2 moles of NaOH, so that's why we put 2 over there. These are so-called mole relationship directly from the balanced chemical equation from the corresponding chemical coefficients. So that's step 2. Step 3, we convert moles of NaOH into liter of NaOH. So to cancel this out, mole should be at the bottom, so this units can be cancelled out. Liter should be at the top. Similarly, for the molarity of NaOH, 0.125 molar of NaOH can be written as either 0.125 mole of NaOH over liter of NaOH, or it can be written as the liter over the top and 0.125 mole NaOH at the bottom. So which one are we going to use? The mole of NaOH should be at the bottom, which means we're going to pick this one. So 0.125 molar. Okay. After you do this calculation, this gives us 0.630 liter of NaOH. And this is how much NaOH solution we need for this reaction. Let's wrap up this chapter with colligative properties. Colligative properties are the properties that only depend on the number of dissolved solute particles, but not on the type of solute particles. For example, if you have 0.50 molar of NaCl solution, and you have a 1.0 molar of a glucose. Remember, NaCl is a strong electrolyte, so this will dissolve in water and it makes 2 ions out of each unit. So the total ion concentration for 0.50 molar of NaCl will be 1.0 molar of the total concentration of ions. However, for 1.0 molar of glucose, it does not ionize. So the concentration of the solute will stay as 1.0. But because the total concentration of the solutes are exactly the same for both solutions, so they will give you the same colligative properties, because colligative properties depend on the number of dissolved solute particles, but not the type of solute particles. It doesn't matter if it's a molecule or ion. When you add a non-volatile solute, the one that does not readily evaporate, to liquid, this will raise the temperature range in which the liquid remains as a liquid. The melting point will become lower, and the boiling point will become higher. These effects are called the freezing point depression because it is lowered, and the boiling point elevation because it is raised. Both the freezing point depression and the boiling point elevation are examples of colligative properties together with osmotic pressure. In order to calculate the freezing point depression and the boiling point elevation, the concentration of the solution is usually expressed as molality. Remember, this is molality, not molarity. They are totally different. Molarity, as we previously learned, is defined as the mole of solute divided by liter of the solution. However, molality, simplified as M, is defined as mole of solute divided by kilograms of solvent. So the unit M is the same as mole per kilogram. The lowercase m is not a mass, rather it is the unit for molality. With the molality, we can calculate the change of the freezing point by the molality times the Kf, or the freezing point depression constant. The change of boiling point can also be calculated by the molality multiplied by boiling point elevation constant. Please note, in both equations, the m represents molality, not masses. Let's work on one example. Calculate the molality of a solution containing 17.2 grams of ethylene glycol. Remember, to calculate the molality, you will need moles of the solute and the kilograms of solvent. So first, let's calculate the moles of solute by using the grams divided by molar mass. This gives us moles of the solute. And the kilograms of water is 0.50. So we substitute the numbers in. We get the molality to be 0.554 molal. M is read as molal because it comes from molality. So remember, in automobiles, antifreeze not only prevents the freezing of coolant within the engine blocks in cold climates, but also prevents the boiling of engine coolant in hot climates, because the freezing point is lowered and the boiling point is increased when a non-volatile solute is being added into water. Let's look at another example. Calculate the freezing point of 1.7 molal ethylene glycol, which is used for automotive antifreeze. The change of the freezing point is the molality times the freezing point constant. The molality is provided together with the freezing point depression constant. So we find out the change of a temperature is 3.02 degrees. Since freezing point is decreased, so the original freezing point of water is 0 degree. Minus the change, it gives us the current freezing point, which is negative 3.2 degrees C. Let's work on an example for boiling point. Calculate the boiling point of 1.7 molar ethylene glycol. The boiling point elevation constant is given over here. So the change of boiling point is the molality times the boiling point elevation constant, 1.7 times that constant. That gives us the change to be 0.87 degrees C. But we cannot stop here because that's only indicating you the change of the boiling point. The boiling point itself is increased from the original 100 degrees Celsius plus the change. This gives us the new boiling point, 100.87 degrees C. Osmosis is another so-called colligative property. Osmotic pressure is the very reason why the flow of the solvent from a less concentrated solution is going to the more concentrated solution. It occurs when the solution containing the high concentration of solute draws solvent from the solutions containing a lower concentration of the solute. For example, seawater is considered as a thirsty solution because as it flows through the stomach and the intestine, seawater, because of the high concentration, actually draws water out of bodily tissues, promoting dehydration. So when you get stranded on the sea, never drink seawater because you'll get crazy very soon. In an osmosis cell, in the very beginning, you have the same height of the liquid level. After some time, the water actually flows through the semi-permeable membrane from the less concentrated solution to more concentrated solution. As a result, the fluid rises in one side of the tube until the weight of the excess fluid creates enough pressure to stop the flow. This pressure is called the osmotic pressure of the solution, as we just mentioned in the previous slide. Osmotic pressure, like a freezing point depression and a boiling point elevation, is also a type of colligative property. It depends only on the concentration of the solute particles, but not the type of the solute. The more concentrated the solution, the greater its osmotic pressure. The membranes of living cells act as semi-permeable membranes, which means the water can move freely from one side to another, but salt or other solute molecules cannot move freely between two sides. It cannot go past the semi-permeable membranes. If the red blood cells are put in different solutions of different concentration, you can expect to see different phenomena. When the solute concentration of the surrounding fluid is equal to that within the cell, which is about 0.9%, there will be no net osmotic flow, and the red blood cell exhibits a typical shape as you see over here on the left side. But when the cell is placed in pure water, the osmotic flow of the water into the cell will cause the red blood cell to swell up. Eventually, it will burst, as you see in this situation. The opposite is also true. If a cell is placed in a concentrated solution, and the osmosis will draw water out of the cell. So the cell will shrink, as you can see in the situation over here. In the three situations we just talked about, the solutions having osmotic pressures less than that of a bodily fluid is called a hypo, which means below, hypoosmotic. These solutions tend to pump water into cells. The solutions having osmotic pressures greater than that of bodily fluid are called hyperosmotic. Hyper means above. These solutions tend to take water out of cells and tissues. Intravenous solutions must have osmotic pressure equal to that of a bodily fluid. These solutions are called iso, which means equal, isoosmotic. When the patient is given an IV in hospital, The majority of the fluid is usually an iso-osmotic saline solution. A solution contains 0.9 grams of table salt per 100 milliliter of solution, or 0.9% salt level. So that's it for today. Have a good day. See you next time.